In this three-part tutorial, we're going to focus on creating a starry night sky in Unity like this. Don't worry, I've exaggerated the size of the stars for the sake of this video because I'm worried about YouTube's compression. They look absolutely amazing in Unity. In this first episode, we're going to focus on reading in the data from a data source ready to be plotted. Let's get started. We're going to start with the standard 3D Unity project, which I've called Starry Sky. On the camera, we don't want a skybox, so change that to a solid colour and set it to black. Excellent, we're nearly there already. The first thing we're going to need is to read in some real-life star data. For this, we're using the Yale Bright Star Catalog. A link for this is available in the description below. This contains details about the 9,110 stars that are visible to the naked eye, presumably on a good day. So let's create a folder called Resources. This is a special Unity folder name which will allow us to reference the file in the code. In here we put our BSC5 file, which is the binary encoded catalogue, so it's nice and small, with just the features we want. I'll explain more about the structure of this as we're processing it. So create a scripts folder and add a new script called star data loader, and we'll dive right into that. First of all, you'll notice I've removed the monobehavior inheritance because we're just going to use this class to manage the data. So what does the file look like? From the Harvard website, you can see that there is a header followed by star data. So let's create a load data method to read it in. This will be a list of type star, which we'll define later. Firstly, we create an empty list of stars to return. Then we want to read in the file. I've just hard-coded the file name here into a variable. We use resources.load to get this from our special resources folder, and we load it as a text asset because that's as good as it gets with C# and Unity. I come from a C background and doing binary file reading is trivial, but here in C# land we need to jump through a few hoops. So we set up a memory stream for our text asset, which we need to treat as bytes. Then we pass it into a binary reader. The file starts with a header that tells us what the binary format looks like. The header is defined like this on the Bright Star Catalog website. So what this is telling us is that every field in the header is defined as a 4-byte integer. That's the integer times 4 bit. For our binary reader, the method we need is readInt 32, 32 bits being 4 bytes. So we do this for each of the fields: sequence offset, start index, num stars, which as you can see from the right is negative because the coordinates are from the year 2000 rather than 1950. Star number settings, proper motion included, num magnitudes, and star data size. Now we could design something to cope with all of these fields and thus other star files from the same source, but that's a bit overkill. So the only one we actually need to use is num stars to iterate over the data that follows. Again, we need to understand the data format that follows. This is shown on the website like this. The catalogue number is a 4-byte real, which is a single position floating point number, which we get via read single. The right ascension is how many radians around the circle this star is positioned at, which is a double position floating point number, which we get via read double. Next is the declination, another double. This is the height above the celestial equator. The following 2 bytes define the spectral type, which is used to infer the colour of the star. I've done this as 2 separate byte reads, as they are a letter followed by a number, so this just makes it easier to process. Next is the magnitude, which is how bright the star is, stored as a 2-byte or 16-bit integer. Note that astronomers record this to 2 decimal places, and rather than using a float, they just multiply it by 100 so it can be a short integer. You'll often find little optimizations like this in binary packed files, so it's worth looking carefully at the definitions. The final 2 single position floating point numbers determine how the stars move across the sky, because even though they're far away, they're not stationary. So we'll take all of these parameters and pass them into a star constructor, and add this to our list and return it. So to make this work, we'll need to make that star data class. Here I have the class and the constructor. First, for the catalogue number, let's save this to a public variable, as we may want to access that. For the position, we'll save the right ascension, declination, and the 2 associated proper motions to private variables. We have no need to access these directly, as instead we just want to know the vector 3 position where the star is. So we'll create that public variable and call a getBasePosition method to calculate it. We'll come back to this function in a moment. Let's just finish up with this constructor. Next thing is the colour. Again, we want a public colour, which will be some function of the spectral type and index. Finally, the size will be a float and proportional to the magnitude. So those are our three key functions. Let's dive into the position first. To start with, we'll ignore the proper motion of the stars. The position in the Bright Star Catalog are the positions on the 1st of January 2000. That's good enough for me. Maybe in the full code in GitHub, I'll include an extra function that will calculate the correct position given the date if you want to be 100% accurate. So we need to take the right ascension and declination angles and convert these to points in world space. The right ascension is the number of radians around the celestial horizon. So we can map that to our XZ plane in Unity. Let's start by just placing them on the unit circle. Here, good old Pythagoras is our friend. Imagine a circle, that's where we need to put our stars. What we know is the angle here, RA, for right ascension. It's given in radians, and our trigonometrical functions work in radians, so all is good there. We don't need to convert to degrees or anything like that. So let's take our angle and draw in the right angle triangle associated with this. We can label the radial line as the hypotenuse, it's the longest. Then the other line with the angle is known as the adjacent, and finally we have the opposite. You can see from this that our desired x value is the adjacent and z will be the opposite. I learnt this as SOHCAHTOA. Sine theta is opposite over hypotenuse, cos theta adjacent over hypotenuse, and tan theta is opposite over adjacent. For simplicity, we can just work on the unit sphere of radius 1. We can scale the star field out to wherever we want in Unity later. This means that the hypotenuse is 1. So we simply have adjacent x equals cos of the right ascension, opposite z equals sine of the right ascension. Following a similar logic, you can work out that the y value is sine declination, as declination is the radians above the celestial equator. Now, if we'd been bothered to create the logic to plot these beforehand, you'd have something that looks like this in Unity. We've got a cylinder rather than a sphere. This is because when calculating our x and z values, we need to taper them in as we move away from the celestial equator. We use the sine to get the y coordinate, and following the same logic we had before, the cos of the declination will tell us how to adapt our x and z values. As we're on the unit sphere, we can just multiply these two values together, and that works out great. I'm not going to dwell on the maths here. Please do take the time to understand the derivation of the coordinates if that's something that interests you. So here's a sneak peek of what that'll look like when we get there. Awesome. So the next thing in our star constructor we need to deal with is the colour. We have a spectral type, which is something like F3, and we want to turn this into a nice colour. I have found this great paper on arXiv called Digital Colour Codes of Stars, which is linked in the description below. Here they've mapped all the spectral types to hex colour codes. Now I don't want to copy in the whole table, so what we can do is just create an array of 8 colours. These will be the colours for the lowest value in each spectral type. So for the first 7 we have O1, B0.5, A0, F0, G1, K0 and M0, and then we add an extra one, M9.5, as the end point. Unity wants the colours to be floats, so I've just created an int colour helper function to convert these for me, so I don't have to have divides everywhere. It also means I can sneak in the British spelling of colour in there. Great, so now we've got those, we want to map our letter number designators to somewhere on this spectrum. So we'll just do a horrible if-else to map the character codes of O, B, A, F, G, K and M to the colour index we need. We have to do this as they're not in alphabetical order, so I can't use their ASCII codes or anything like that. If we've got something unexpected, we'll just make the star white. For everything else, we want to linearly interpolate the colour between the colour of this category and the next, dependent on the number, which I call spectral index. So we just map 0 to 10 into a percentage and pass that to colour.lerp along with the 2 colours we want to interpolate between. Again, here's another sneak peek of our final stars with the colouring added to them. I think this really adds some dynamics to your sky, though you may want to tweak the colours slightly and push them more towards white. The final function we need for our star constructor is to set the size. There are a bunch of ways that you could take the magnitude, which represents the brightness, and work out how we want the star to look. I've taken the simple approach of just adjusting the size. You could actually take into account the colour here, or play with the colour alpha to do this, or realise that the brightness is proportional to the area and do it correctly, but I actually think this simple method looks good enough. So what we want to do is map the weakest magnitude to be size 0 and the strongest to be size 1. We can do this with an inverse lerp, which we invert because actually the most negative magnitude is the brightest. You can't trust astrophysicists, it seems. Now the file is fixed, so I've cheated, and I know the smallest is -146 and the largest is 769, so I can just put the values in there. If you wanted to be robust, you could iterate through the file to extract these, but it's not really worth it in this example. And that's it. We're finally finished with reading in the data and extracting the information we want. So a final sneak peek. All this setup we've done here will enable your stars to look like this once we've created the game objects. I hope you found this tutorial useful so far. As ever, the full code is in GitHub and linked in the description below. In the second episode, we'll use this star data to create the objects you see here. See you next time.